And let me introduce Dr. Urban, and he will tell us about his department.
So, hello everybody. I will say something quickly about the AI department. It's a department that is one of the youngest. We are 2 or 3 years old now. We were created by merging basically four groups. So the machine learning by Robert Babuška, Tomáš Mikl, the foundation of AI, Mikuláš and transformal methods, and Martin Suda, automated reasoning. Currently, we have about 11 researchers of various seniority and about 60 full-time employment equivalents. In total, we oversee about, or co-supervise about 12 PhD students, but those may be also at other universities. Four of them, yeah.
Já tady mám join audio.
Ne, svůj reprák normálně, aby to přestalo mluvit. Tady tohle, aby přestalo. Tadyhle to
zmenšat.
The echoes from the audience.
To není moje.
Okay, so everybody has to switch off his loudspeaker, okay? Is it better now? No. Somebody has loudspeaker on. Is it better now? Yes. Thank you.
Well, it could be use the microphone. Okay. Yeah, so four of them defended, which is sort of a lucky start. We don't have so many advanced students. In total, there were about 44 papers published, and we applied for about 10 projects as PIs, which were funded, some were rejected, some are still being evaluated. As usual, Martin Suda won his category of the World Championship in automated theorem proving with the LPAR system. And we have a new Marie Curie Fellowship, which is a relatively prestigious grant obtained by Jonathan Huerta at Unive. We organized 3 conferences, 2 of them here, Thibault and Focus, and 1 workshop. And Tomáš Mikl is working on a startup, so we wish him good luck. There were a couple of invited talks, especially Tomáš Mikl really went into an overdrive with media appearances and lobbying for AI. And also we had many visitors at 2023 because it's big fundings were finishing and we had a lot of travel money. Here is a selection of papers, so the top 3 are in journals. You will hear in more detail about some of them. So let me just mention the one that will not be presented because Barbara Utsova couldn't make it today. So that's like a new collaboration with the team of Lenka Zdeborova in Switzerland, which, like these physicists, they can publish in very high-impact journals, so it also looks very good in this check system. And again, like from the remaining conference ones, let me quickly mention this VISAR 60 for VISAR 50. It was really like a final publication about the ERC project that I had, where we basically increased by 50% the performance of the automated theorem viewers over the situation 10 years ago. So that's sort of concluded some challenge. And that's it for me. That's the quick introduction. And now I will switch to Zahálka, who will give the first presentation.
So let me try to make it full screen.
It's the second, the context menu on the side. The one on the right. Oh yeah, presentation, yeah. One.
Okay.
This works. Hello everyone, welcome to my talk titled Interactive Multimodal Learning with Exquisitor, the Influence of Interaction Strategy and Late Fusion. It's work that I have completed with my former PhD student, Marsh Baskan, and Professor Björn Olsson, both formerly at ITU Copenhagen, presently at Reykjavik University. So what is interactive multimodal learning? It's a niche machine learning discipline. If you're familiar with the term relevance feedback, you should be right at home. You can imagine it basically as classification with dynamic class definition that is up to the user. So instead of having a fixed class dictionary beforehand, the concept of what is relevant and what is not relevant is up to the user, and the model is supposed to learn it on the fly. The typical use case for this is forensics. So, for example, a forensic investigator is looking for to solve a case, but what data is exactly relevant, of course, differs case by case. So the model has to be flexible. Yeah. So first you take your data, you extract and quantize your data representation, and then each session starts perhaps with some random data. The user provides some feedback that goes to the model, which gets trained. Then it ranks the data and produces relevant data suggestions to display in the next interaction round. So the move that you see is called an interaction round, and the session keeps going until the user is satisfied or dissatisfied and ends the session. The interactive part means that the red highlighted part, basically the entire interaction round, from the machine standpoint, has to complete in up to 1 second, which is quite challenging for large data sets. And the multimodal part is that we have multimodal data, which of course has some bearing on how we display the data to the user. So previously, in our previous work, we have contributed a state-of-the-art interactive multimodal classifier, which is able to complete one interaction round in 0.3 seconds on 100 million images with multimodal information, only utilizing a single CPU core. And my talk today is going to be, I'm going to give some interesting intuition from older work, that's one slide, and then move on to the recent work, the reason why I'm here. So recently we have looked at interaction strategies. So how the user produces user feedback and how the user labels get to the model. And for the learning people among you, there might be a bit of a surprising intuition. So the common sense would dictate that we add as much correctly labeled training data as possible, but that turns out not to be the case. It's better to add a limited number of representative positives and a large number of negatives. So if we are faced with the final needles in the haystack task with blurred boundaries between positives and negatives, or what is relevant and what is not relevant, we might be better off even exploring with sampling a larger number of random negatives. So this task, again, common in the forensic context. And now for the main course of this presentation. So that's work that has been published at IMuR in November 2022. So there we look at the influence of late fusion. So namely, how the model ranks the data and how it produces relevant data suggestions for the next interaction round. So this work is in the context of videos. So we have looked at two modalities, visual modality and audio modality. But for simplicity's sake, we basically subdivide the visual modality into other modalities. So we look at the image content, the scene context, action information, and the audio modality. We have 3 video data sets. Each is biased towards single modality, and one modality is missing from each data set. So the first data set is V3C1, used in the TrackWeight 21 challenge, which is biased towards image, and the audio is missing in this data set. Charade is heavily leans towards action, and again has no audio. And the third data set is an audio-visual data set, VGG sound, where audio is the most important modality, and the scene context is irrelevant. The task that we've been investigating is ad hoc video search. So to find as many video frames or segments that match a text description as possible within a certain time limit. Now, I said that this is about fusion. So what does that mean? So of course, in our task, we want like a single result from information in multiple modalities. So the term modality fusion deals with the strategy, like when do we actually merge the information? There are 2 basic approaches. The first is early fusion. So we concatenate either the data or the base feature vectors that are extracted from the data, and we train a single model. The second one is late fusion. So we train models for modality and aggregate their rankings only towards the end. Now, which one is better has been shifting over the years somewhat. So for a long time, the established practice was to perform late fusion in multimodal research. But nowadays, early fusion seems to be the go-to because deep nets and especially end-to-end models are very comfortable with you checking in the data and getting the label at the end. So, of course, this begs the questions, why do we investigate late fusion in the first place if early fusion seems to be the dominant approach? And we have a reason for that, of course. So the machine learning or multimodal computer vision state of the art is determined by offline models that have fixed definition tasks, as I have talked about in the beginning. So the classification of the fixed file dictionary. And we have mentioned that that in interactive analytics, the concept to look for may be vague, or its definition might not be known beforehand. So late fusion adds flexibility here, and if certain modalities should be focused on throughout the system, the interactive model can adjust the modality weights dynamically. So the research question of the paper was that, so suppose that we have our models per modality and they rank frames by relevance. So which frames do we actually show the user in the interface, here conceptualized as a 3x3 grid? So the default option is to perform no fusion at all. So we just split the interface into n modalities and show the mini rankings. The natural multimodal option is what we call full fusion. So you perform rank aggregation, possibly weighted, and then you display the results of that multimodal ranking in your interface. And the third option is a hybrid. Part of the interface does one thing, the other does the second thing. So this has been a highly experimental work. So I'm just going to give you like a really brief rundown. We have experimented with 24 frames per interaction round. We have evaluated the 3 configs that I have just defined, and we have considered essentially 4 configurations of the fusion algorithm. So first is unweighted rank aggregation. So all modalities have a weight of 1, so their rankings contribute to the final ranking equally. And the second one is weighted rank aggregation. So for each modality, we have set its weight to 2 and the others to 1. So that yielded 4 configurations total. And the evaluation metrics were average precision and recall over 10 interaction rounds. So this would be the early phase of the interactive analytics. And again, not to barrage you with too many tables, we got some nice intuition out of this. So if you know beforehand that your data set is biased towards a single modality, then you should be using full fusion. So you just produce a single ranking and display that with weighted rank aggregation biased towards that modality. If you're exploring an unknown collection where you don't know which modality is going to have the dominant effect, you might want to consider partial fusion with unweighted rank aggregation, and you should be fusing. So no fusion was the clearly subpar approach. To conclude, so this work has concluded our Exquisitor interactive multimodal learning research. Umar got his PhD, so that's great. Over those years, we have contributed a state-of-the-art interactive classifier, enhanced intuition about interaction strategies, and knowledge how to conduct multimodal fusion properly, which has been the topic of my talk today. My present research topics or research interest has shifted somewhat towards AI security and resilience and robustness of AI in robotics. I'm excited to contribute in the context of the RoboProx and CoreSense projects. And finally, I now publish an R&D blog with new posts every 3 weeks about AI security topics. So if you feel interested in this topic, please feel free to visit. That's all from me, and thank you for listening.
Oh, okay.
No questions?
Yeah, there could be some questions.
There's a question, okay? Yeah.
So when you present these 9 or 24 results to the user, you somehow make sure that they are complementary, that they are not very similar results from perhaps the same source field.
So you mean that multiple of these models will yield the same item in the ranking? So you just display it once and then you kind of skip one ahead in the following rankings, basically.
I mean, or two neighboring frames from the same video. Can this happen?
That can happen, but that depends on how you extract the frames. So this is a strategy that we haven't considered explicitly in this work, but it might be worthwhile to extract key frames instead of going frame by frame or just running FFmpeg with a set interval. So yeah, but indeed, if you would sample with very short intervals, then you would have this effect. Absolutely. Thanks. Yeah, question.
Thank you. My name is David, and I will be presenting our paper presenting semantics in textual adversarial attacks. So, what is the motivation behind this? Today, we have a large amount of data added on the internet daily, And basically that makes it impossible to manually moderate the content on the social networks and the forums and the other stuff. So basically we need to do that automatically, and usually we employ some text classifiers which are able to identify harmful content. Unfortunately, they can be attacked but through the adversarial attacks, and that's what my work is about. So how does the adversarial attack on a text classifier looks like? Because we usually see, or most of the audience is familiar with the adversarial attacks in the computer vision, where you have some invisible perturbation to the image, and it makes misclassify the image. But in the text, you cannot do some invisible change. So what you usually do is that you introduce some white spaces or you change few words. So we can have a look at example where, let's say, we have a movie classifier which classifies if the movie is negative or positive. And on the left, we have the movie review. I just wasted 2 hours of my life, do not watch this movie, which is classified as a negative movie review, which is obviously true. But if we change few words, we substitute watch to see and movie to film, now it's classified as a positive movie review, but it's still negative movie review. So we can consider it as an adversarial attack. So what are the requirements to consider attack as a successful? The attack has to have a human prediction consistency. So if the movie review was negative, it still has to be negative even after modifications. Then it has to have the same meaning, and then it should have a language fluency. But what happens is that the second condition is usually not fulfilled, and the semantic similarity is broken. So we can have a look at the example where we have the sentence, the best film ever is film matrix. And then we substitute the best for the verse, and then obviously it's classified as a negative, but it's classified right because it's a really negative movie review, so we cannot consider it as a successful adversarial attack. And what we show in our work, that up to 70% of these adversarial examples can be discarded because they do not fulfill the second condition and they change the meaning. And the problem lies in the similarity metric, because what these approaches do, that they map these two sentences into embedding space, and then they measure crossing similarity, usually with universal sentence encoder, and it doesn't work as it's intended to do, because we can see that in the second row, this movie is so good and this movie is so bad, has a high cosine similarity, but this movie is so good and is so tasty, has a lower cosine similarity, which shouldn't be like that. And we can even see it in the example, like universal sentence encoder maps similar words into the similar embedding space. But with our approach, which is called SPE, we are able to tackle this problem, and we are able to map opposite words into different vector space. So why this keeps happening? Because like typical encoders, like word2vec or universal sentence encoder, are trained with the skip graph technique, and that means that the words or sentences which appear in a similar context are mapped into the similar embedding space, because you are trying to predict the middle word. And our approach is to substitute this universal sentence encoder with our technique, where basically we take the advantage of already pre-labeled data sets. So we are taking the advantage of human supervision, and we are not predicting the middle word, but we are predicting the label. So that means that words that are most discriminative for a given label will be close to each other in the vector space. So that means that opposite words shouldn't be mapped into the similar vector space. We can see it in the table in the last example. This movie is so good, so bad. With the use had a high cosine similarity, but with our approach, it has a lower cosine similarity, and it's closer to the truth. And how we've done that, we've trained several classifiers on several data sets, and then we combined it into the one robust vector. And that's it. So right now we cover the experiments for that, and I will just say that we basically do most known and state-of-the-art textual adversarial attacks, and we've substitute their sentence encoder with our technique, and then we've measured what happens. So from the results, we can see that our sentence encoder has much higher attack success rate than the other sentence encoder. In some cases, it's up to 5 times better, and we are also much faster than the others. So to sum it up, almost up to 70% of adversarial examples of text can be discarded because they are wrong. With our technique, it's much better, but it's still not perfect, and we were able to improve the accuracy and the speed. And lastly, we release our code as open source so everybody can immediately use it in their work. That's all from me. Thank you. Well, yes, because with this technique, you can basically make the adversarial attacks better, but thanks to that, you can also make defense better, because when you have a better attacks, then automatically even better training data, so you are able to make even defenses better, so it's applicable even for these defense purposes. Thank you.
Hello, I'm Thibault Gauthier, and I will be presenting the paper Island Coding Program Synthesis for the OES, which is co-authored with Mirek Olszak and Josef. So let's start with a simple brain teaser. 0, 2, 4, 6, 8, 10. What comes next? Well, the obvious answer is 12. But why is 12? Couldn't it be 13 or 11? The reason is that we are looking for the simplest explanation for this sequence. And this is known as Occam's razor in science. Like, the simplest explanation is likely the best one. Here, the simplest explanation will be written as a program. So our simplest explanation here is f of x equals 2 times x. So you see, you can compute the sequence. F of 0 is 0, f of 1 is 2, etc. F of 5 is 10. And then we have the right prediction, f of 6 is 12. But if you make the program longer, and you say instead of 2 times x, you say 2 times x modulo 12, then you get f of 5 is still equal 10, but f of 6 is 12, modulo 12 is 0. So we get the wrong answer. This is something we know about the natural world, and some heuristics we know. And we'll be using this heuristic to try to find explanations. So we like simple explanations, no? So we will try to find a simple explanation for mathematical objects. So we will be looking at integer sequences, because integer sequences are very common in mathematics, and we like mathematics. And here is a very famous sequence. It's the prime numbers. So it starts 2, 3, 5, 7, 11, 13, 17, 19. It doesn't seem to have a very regular pattern. And its content is part of an online encyclopedia of integer sequences that was compiled by a mathematician like Sloan since 1964. And it contains more than 350,000 sequences that are interesting for mathematicians and from various domains. So now we'll be asking some language model to tell us, given the sequence, what is the explanation. We are starting from a completely random language model, so it will start to output a random thing, but it will find some solution for a simple sequence like the one I showed you at the beginning. and then it will learn from the solution it has found. And then it gradually learns. After 500 iterations, we have solved for more than 100,000 sequence. So let's continue with the prime numbers. So if we give the prime numbers, but only up to 271, it will come up with some nice mathematics, and which is called the Fermat primality test. But this is not correct, because it will say that 341 is prime, but 341 is not prime, because 341 is 11 times something. You can guess. Now we, if you add some numbers to the sequence, then it finds the correct answer, and it works for all primes. So this is called the Wilson primality test, although it's less efficient than the first test. So now let's see some example of solved sequences. In this library, there are various domains. So we can talk about primes and twin primes. It can talk, we also solved some problems about Diophantine equations, or the next problem is about automata theory, like game of life kind of thing. And this last problem is about real numbers and maybe about pi. And you can find all the programs, and some of them are quite long, on this link, if you want to look at them. And finally, I want to show you a very long programs that we have found. We try to find the shortest program, but sometimes there's some necessary complexity, and the program has to be long because the explanation is difficult. So here we are looking at some kind of numbers that can be written as p times q times r times s squared, where you have distinct prime p, q, and r and s. And that's the sequence that is generated. Below is the program that we have found. Maybe there is a simpler program. Maybe it's not the best explanation, but this is the best we could find. And this is some encoding we give to the language model because we don't want to give it parentheses and commas. Thank you very much.
Any question? There's maybe more of a comment. I'm not sure pocket radar is the right thing, but CACORR complexity is what you're looking for. That's the definition of the complexity of something is the complexity. Smallest program that generates.
Yeah, thank you for the comment.
Hello, I'm Chvalovský, and I'm going to present our paper Guiding an Instantiation Improver with Graph Neural Networks. It's a joint work with Kostya, Yela, and Josef. And what are we interested in? We are interested in an automated theorem proving something that's used in, let's say, software and hardware verification and also in formal math. Here you should think about some kind of a research mathematician working in some group theory who wants to prove his or her famous identity. That's a task where really computers outperform easily humans. So in this particular thing, what we are interested in is in guiding one particular theorem prover called iProver developed by Kostya. And it's a very strong theorem prover for first-order logic with equality, something you may know under the title predicate logic. And it's using, among other methods, simple instantiation. And instantiation is a method that makes it possible to employ also solvers for weak logic, like proposition logic, where you have very powerful subsolvers, and you can use it to prove something in first order logic. And usually it works like that you want to generate some consequences, And for that, you select the most promising formulas. And what we want to achieve here is we want to really guide this proof search by selecting best possible formulas. So how it looks in reality in such a theorem prover, you split your formulas into two groups, so-called process and unprocessed formulas. Usually there are formulas of special types or clauses, but let's talk about some general formulas. And what it means, in unprocessed set, you have some kind of consequences you have obtained, whereas in processed set, you have like things that you believe should participate in your proof. So you always want to select some best thing that you have derived and produce all possible consequences with previously selected things. These sets are usually quite big. This one can be like of size of, let's say, thousands of formulas. This one, let's say, size of millions of things. So when you want to really derive something, the crucial thing is to select right things for producing new consequences. That's what we want to guide. So when you derive new things, what you usually do is you add some scores. And people did it manually, like usually, show things are better. You want to also take into account derivational history and things like that. So people have been able to develop various heuristics how to do that. But we have a lot of data, so we should do somehow better using some other models. So that's basically what Josef and Jan kind of started with in their Enigma style theorem proving when you really want to learn some kind of a model for this selection process. And this has been used quite successfully in some state-of-the-art automated theorem provers. When Josef talked about his YARS project and some improvements, this is basically not mainly, but substantially due to these things. And then right now what we kind of using are some kind of graph neural networks because we have sets of formulas. So it means that we have some kind of structured data. So we have graphs and let's use graph neural networks. But we don't, call graph neural networks directly from our provers because it has some kind of technical issues. So what we usually do, we start some kind of a server that communicates with the prover. So we use some kind of client-server architecture, and then server can use GPUs and all that. Of course, it slows down things, but it's beneficial for some other reasons. So that's what we also do here, and we had to come up with slightly more complicated server than usual for some reasons. There are some new ideas in this paper, but one kind of interesting one is how we create print examples. Usually it looks like when you find a proof, you have a set of process clauses, process formulas that are, formulas that you believe should be the best for finding your proof. But once you do that, actually, what happens is that only a small part of these formulas are actually used in the proof. Majority of things you selected are not used. So you can think about these that were used as positive examples and that these that were not used as negative examples. And you have like a training example, one per example per proof. We know that this is not good because it's not how it works actually when you are really looking for a proof. You don't know the whole set that you get just at the end. It's developing along the way, but it was kind of very useful proxy for us for quite a long time, and it worked nicely. But because we had to do some other changes, we decided, okay, let's do now training examples properly. Really, using the queries we asked during the proof search as training examples, and we did that, and surprisingly, it helped a lot. We knew that in advance, but we were kind of surprised at how much it really improved our stuff. So what we have some kind of like, let's say, data, some kind of a MESA data set, some kind of formal mathematical library, and we want to prove something over that. And if you take iProver in instantiation mode with some human developed heuristic, it's able to prove 500 problems. if you slow down it by communicating with server but still using these scores, it solves like 880 problems. And if you are on our development side, and if you even evaluate it using GNN, graph neural net, it slows down things into like 450 problems. So for this whole approach, you get 10% less problems in 15 seconds when you run your solver. So you have to overcome this to get something meaningful. But you get some proofs along the way. You can train your GNN on them, and you get significantly better results. What it means is data, this is like we are using data based on proof that all type of generating training data. When we use this new type of generating training data, we get way better results. But what's also interesting is, what you can use the scores provided by your GNN and use them, to select the best clauses. But what usually worked better for us was combining these scores with, scores that are given to us by heuristics developed by humans. Combining these two things together work best. And that's what you can see here, like, the scope mode, it's very combined, it works better than just using, scores from GNN. But when we train it now for another generation, so we take proofs, we get before and train another GNN, we find out the best model is now the one that uses just GNN scores, completely ignoring the whole scoring system, which was a bit surprising. And if you do it for another iteration, you get even better results. And now you can also take into account some, for example, a bigger graph neural net, and you get even better results. So what we end up with, they improved more than twice the original performance of iProver, in instantiation mode, still running in 15 seconds, doing some kind of a fair comparison here. What's interesting that our old, method how to produce training data performed very worse, and in this particular thing, still the cooperation between GNN and human developed scores is better thing to do. Whereas here now GNN, using just these scores, you can outperform the original performance, original iProver. So what's the conclusion? Well, we really managed to improve iProver quite a lot. And what's interesting that we can really do that in some real world scenario, time limit is fair. We are really, this client server architectural evaluation of our GNN, it's all taken into account. It slows things down, but it helps a lot. And what is kind of really surprising that this very simple trick that producing, better training data worked way better than the original approach, which was okay. We were very, satisfied with that for a long time. So it was kind of interesting conclusion for us. Thank you.